Okay, everybody. This is a quick review of asymptotes, which will then lead into the first new lesson that we will be doing. So a little review of asymptotes. I think I did this before school ended, but that was 3 weeks ago, so it doesn't hurt to do a review. So first kind that you encountered in grade 11, I believe, vertical asymptotes. I'm going to shorthand as VA. Formal definition would be the limit as x goes to c of f of x equals plus or minus infinity, which, as you know, on a graph, the graph spins out to infinity. The simpler version that we kind of go by is what makes the denominator equal to 0. So for instance, an example, very straightforward, 3 over x minus 1, the vertical asymptote would be x is equal to 1, because that makes the denominator equal to 0. All right. Then you learned about horizontal asymptotes. Again, I'm going to abbreviate them HA. Formal definition is what is the function doing as you go to positive or negative infinity. There were three rules that you learned in Math 12 for that. I'm going to quickly summarize them. First one was if the numerator degree greater than the denominator degree, you get no HA. So the example that they always use, that you would see would be f of x is equal to x cubed plus 1 over x squared. No horizontal asymptote. Formally, if you're doing the limit definition, this one over here, if you did the limit as x goes to infinity, and remember, we don't look at constants, those are irrelevant, so we would just simplify it to this, which would then become that, and you can see if you put infinity in there, you get infinity, therefore no horizontal asymptote. In fact, as we will see in a bit, these sort of cases give you a slant asymptote or oblique, or you can have cubic, quadratic asymptotes, but we're only ever going to be concerned with slant asymptotes, and I'll review how to do that in a sec here. So that's the first definition. The second was if the numerator degree is smaller, so it's less than the denominator, here HA y is equal to 0. Okay, so we can just flip this example. X squared over x cubed plus 1. If you do the limit definition, we know it's going to be 0. But if we do the limit, we can see why it would be. Goes to infinity. Again, don't care about constants. So you're going to have x squared over x cubed, which becomes 1 over x. As if we go to infinity, we get 1 over infinity. Any constant divided by infinity is 0. So if you see the degree of the numerator is smaller than the degree of the denominator, you know right away it will be 0. All right. And then the third type, the degrees of, I'm supposed to have a u in there, numerator and denominator are the same. So f of x is equal to 3x squared over 2x squared. If you do the limit definition, we're going to get the limit as x goes to infinity. These will cancel out, x squared over x squared of 3 halves. Should not have an equal there. Of 3 halves. And the answer would just be 3 halves. In other words, it is the leading coefficients. Pull your horizontal asymptote. Just put it right here. So just one more example. Doesn't matter what the numbers are or how many terms. That the degrees are the same. So if I said the horizontal asymptote, you would just tell me it is the leading coefficients, 3 over 7. Okay. So we mentioned up here that you had a slant asymptote if the numerator was greater than the denominator. Well, how do you find your slant asymptote? Sometimes called an oblique. So we'll use this term x squared minus x. Sorry, that looks pretty ugly. Over x plus 1. We do division. So you can do long division, which I know everybody likes. The thing about long division is it always works. Remember, you have to add in the 0 because it has to go in descending powers. And then it's how many times does x go into x squared? X times x times x is x squared. X times 1 is x. You're going to subtract them. The x squareds go away. Negative x minus x is negative 2x. Bring down the 0. X goes into negative 2x. Negative 2 times. Negative 2 times x is negative 2x minus 2. Again, subtract. The 2x's go away. And you're left with 2 as your remainder. You always rewrite these as q plus r over d. So our quotient, so what's up there? The remainder was 2, and the divisor is obviously what you're dividing by, x plus 1. So if you think about it, define the horizontal asymptote because this is the same as that, it's just rewritten. So if I want to find my horizontal asymptote, I do the limit as x goes to infinity or negative infinity, doesn't really matter here. And what happens is this, because we have a variable in the denominator and the top is a constant, goes to 0. So you're just left with x minus 2. And that is your horizontal asymptote, i.e. the quotient. As you can see, what's up there? That is all you have to see. Sorry about that. For those of you that don't like long division, we can do synthetic. So a quick reminder of synthetic. Synthetic only works, well, you can use it for nonlinear denominators, but it's really easy for linear denominators. So we take the coefficients, which are 1, -1, put a 0 down for the constant term. We take what makes the denominator here 0, -1, that's your a value. And if you remember, bring down the 1, we multiply these two, which gives us -1, we put that there, add those together, -2, -1 times -2 is 2, -2. That is my remainder. This, because it was a degree 2, is now linear, so that is actually x minus 2 is my quotient. So we get the same answer. All right. Okay, let's move on to a slightly different type of. So this will be new. So if your function has a radical, some strange stuff can happen. Not always, but functions with radicals. All right, so horizontal asymptote. And that's what we're looking at specifically here. So let's do f of x is equal to 3x minus 2 over root 2x squared plus 1. Okay. So if I want to do the horizontal asymptote, we cannot limit as x goes to. Now we got to look at positive and negative infinity because different things can happen. So we don't care about constants, right? I'm shorthanding this. So 3x or root 2x squared. This denominator is going to turn into root 2x. What happens to the x's? Now this is, the top is always going to be positive as we go to positive infinity. So the x's will cancel, and we're left with 3 over root 2. That makes sense? What if we say, well, what happens when we go to negative infinity? Same bit here, because we cancel the constants. Better. So we have 3x root x squared, which becomes 3x over root 2x. Now, negative infinity in the top here, right here, is always going to be negative. So that's actually going to be a -3. The bottom here, this x was actually from here. It was always being squared and then square rooted. It's a positive root, so that's always positive. So the bottom is positive. So the answer when you go to negative infinity is negative root 3 over 2. In fact, when you look at this graph, it looks something like that graph. That is 3 over root 2 as we go to positive infinity. And this is -3 over root 2 as you go to negative infinity. So just be aware of that when you're doing functions with radicals in it. We don't look at it too much in this class, but moving forward, there you can get different asymptotes depending on which direction you're going. I want to show you something. This little magic trick where we cancel out the constants here. There's a reason you can do that. There's actual math behind it. It's not just, let's just do it. So let's look at another example. We'll just do a limit as x goes to infinity of 2x minus 1 over x plus 1. We know the answer is going to be 2, okay? Because we would just cancel those ones. We'd cancel those ones and say, well, it's 2x over x, so we get 2. The reason you can do that is because the proper math, so you take the highest degree, in this case it's 1 for both, and you multiply top and bottom, so essentially this is 1. Essentially you divide the top by the highest degree exponent that it has, which is 1. Top and bottom by the highest degree exponent in the whole function, in this case 1. So what we generate is 2x over x minus 1 over x over x over x plus 1 over x. And remember, we're doing the limit as x goes to infinity, which I should have written there. As you go to infinity, a constant over that means that's going to 0, that's going to 0. That's why the constants go away. What are we left with here? Those x's will cancel. Those x's simplify to 1. So I'm left with 2 over 1, which is just 2. Okay? So that's the actual math behind why you can cancel out constants. All right. I will leave it for there. That was just a review of asymptotes. This new stuff, or actually, let me do a couple more examples. Yeah, 3 more examples. In space, yeah. Okay, I like the blue. So, what if you have a question like this? Find the limit as x goes to positive infinity of x minus squared plus 7. So right away we go, okay, we want to cancel the constant. Well, we get x minus root x squared, square root of x squared is x. We get x minus x, which is actually, because we're doing the limit as infinity, infinity minus infinity, that is indeterminate. Right? Because we don't know which infinity is bigger. It's not 0. So we have to rewrite this. So we're going to rewrite. And we're going to use everybody's favorite. If you remember math, oops, sorry. If you remember math 12, we are going to, when you have square roots, or your limits, we're going to multiply by the conjugate, which is going to be the same numbers, except we've changed the sign from negative here to positive here. The reason we do that is because we create a difference of squares. So when we create a difference of squares, the top becomes x squared minus all this stuff, x squared plus 7 over x plus root squared plus 7. Top simplifies to negative 7 over x plus root x squared plus 7. Again, this is a limit as x goes to infinity, so I'm going to shortcut it here. Don't care about that 7 because it's a constant. So we get x plus root x squared, which is negative 7 over, that's going to be x plus x, which is negative 7 over 2x as x goes to infinity. Constant divided by that is 0. So the horizontal asymptote as we go to positive infinity is 0. If we do, as we go to negative infinity, because you have to check both sides because of the roots, there's our original. We try the simplest way first. So we cross out the 7. We get x minus root x squared, which is x minus x. Oh, I'm ahead of myself here. Let me back up and erase. Sorry, people. So normally we would get to here. This one up here, right? Which we said we can't do. But if you think about this one, putting in negative infinity. So it's negative infinity minus the root of negative infinity squared. Negative infinity squared is infinity. The root of infinity is infinity, and negative infinity minus negative infinity are going in the same direction. Negative infinity. We're not canceling because we're going in the same direction. So as we go to negative infinity, there is no horizontal asymptote. And if you look at this graph, if you graphed it on Desmos, it would look something like this. As we go to positive infinity, it gets closer to 0, and as we go to negative infinity, it just shoots down like that. Okay? So here is the questions I would like you to do from your book. Page 202. Numbers 1 to 5. Just say 1 to 6. 13, 15, 27, 29, 31, 103. And if you needed more help or more info on this bit right up here, the proper method for doing it, just read the chapter that is in this page 202. I think it's 3.6 or something like that. I'm not sure, but you can have a look. It's the chapter attached to this assignment. Email me if you have any questions, and good luck.